All right, everyone. Thank you very much once again for another round of Applied Building Science webinars. Today we're going to be talking about high performance ducted mechanicals. Just a wee bit of housekeeping before we get started. As you heard from the announcement, whoops, you are all in listen
I
only
think that's
mode.
two of us clicking. I'm sorry.
That's all right. If you have any questions, please shoot them through the Q&A. You'll also find that there's a little orange arrow there. If you have any trouble with your audio, I suggest you go there. There's not a whole lot we can do on our end. Sorry about that. Once again, as always, we appreciate your feedback, whether it's through the Q&A, whether it's through a follow-up email later. We do enjoy talking to people, which is sometimes a rare occurrence these days. So please give us your feedback. All right, Mike. And for those of you who don't know me, I'm Joey Starr. I am a technical project manager here at Southface. I help with our weatherization training as well as a few other projects. And Mike, if you want to introduce yourself.
Yeah. And hi, everybody. I'm Mike Barsick, and I'm come at the world from the mechanical engineering side of things. So this is a particularly fun webinar topic, but they're all fun, Joey. I love these things. These are so much fun. And I thought I would kind of share, I don't know, I was looking through some old photos of duct systems, and I found an old picture of me when I was in my younger days. And then I thought I should look for one of you in your younger days. And that's what I came up with. I don't know.
Yeah,
So
the red
anyway,
hair
welcome
grew
back,
out.
everybody, to those who have, yeah. Welcome back, everybody. And again, thanks so much for your participation and for hanging with us. We are Southface. Hopefully you figured out who we are by now, but really appreciate people who are supporting us in this time because can use it. So thank you. I don't know what else do you want to say here, Joey?
Yeah, just, we haven't taught a class in a while and we were really ready to get back and, both for our sanity and for, keeping the lights on. So we appreciate you coming to the webinars. We appreciate you kicking in for the CEUs and everything that you guys have done.
Yep. Yep. All right. So driving on, a big push again for some great resources. One in particular I think might be useful is the Georgia Energy Code Field Guide. All of these you can get from the Southface.org website. And then there's a resources tab that has stuff in it. And particularly some good graphics of, we'll probably see these later today, of air sealing details. And again, here's the big picture, why we think this stuff is so important, and understanding and applying the physics of heat, air, and moisture flow to real world applications. That's why these are so much fun. And the series of webinars that we're on right now, this is I think our 8th one here, and we have another one scheduled for next week. And Joey, then what might happen? That's the question.
To be determined. So we're open to feedback. More likely, it's going to be maybe a once a month webinar where we're going to kind of continue going through some topics. We have a couple of ideas, but we're always open for others. So, but do kind of tune in, stay tuned for our announcements. We'll be emailing that out, and we'll put it on our social media and everything as well. And
Very
just
good, thank you.
real quick, while
Yeah,
we're
so
kind of in housekeeping phase, someone's asking about the documents. I did accidentally forget to put those up today. There's a glitch with the GoToMeeting software. So sorry, no documents. They'll be sent out immediately after the webinar today, along with a recording of this presentation.
oh, okay. All right. So yeah, we have we've burned the PDF. We just didn't get a chance to upload it. And then again, you can get a lot of good information from the Energy Code resources page. So driving on, let's see if I can get it back here. We talked about the house as a system, and again, this one in particular, talking about space conditioning, and of course, we're doing all this because of the people, the occupants that are living in the house. So I'm experiencing a little bit of a delay. Joey, I think we've now figured out this is who is here. If you are not represented by one of those bullets up there, send us a question or a chat message just to let us know. And we'll try to make sure we account for everybody here. But this is our typical audience. And again, grateful for those who show up. Anything you want to add?
No, just keep in mind, because we are kind of casting a wide net here, that we're going to talk about code stuff. We're going to talk about some nitty gritty things. Some of it might be above your head. Some of it might be too remedial, I guess. But just keep that in mind. We're taking the whole picture, and I think that you'll get something out of it in the end.
Hopefully so. Okay. The learning objectives, this is the condensed version. The original version I had, I think we had like 15 learning objectives up here, but we were going to cover them all. So I think that's enough said. We should cover that in great detail. Just a quick back again, heat, air, and moisture. The different ways heat will flow. In terms of forced air mechanical systems, the main one that we're talking about is convection. But also I like that, Joey, you want to explain what your magic graphic is showing us right here?
Yeah, so we don't think about this all the time, but if you the red line now indicates the air barrier. So we don't really think about it sometimes, but the inside of the ductwork, the liner there becomes part of the air barrier as well. So we need to consider that again as kind of this whole building house as a system sort of deal here.
Yeah, and in essence, the building thermal envelope is the duct system. So, we've got R8 on our building thermal envelope if it's going through the attic. Yay. But that's a really good way to think about it too, that it's part of the air barrier and the thermal barrier. Also, this is the equation that I think I forgot to put in our heat transfer one. This is, it's actually a fairly simple calculation. It's if you've got a certain amount of airflow and the air coming in is cooler or hotter than the air that's in the space it's being delivered to, you can calculate the BTUs BTUs per hour that's being delivered. So I had a example. Let's see if it shows up here. So if you got a fan that's pushing 50 CFM of outside air into a home and the home's being kept at 75 and it's 90 degrees outside, so, that's kind of like what's the impact on the load of the house because of, essentially delivering air that's 15 degrees hotter. So you can plug it in the calculation and you can see it's about 800 BTUs an hour. Okay, that was enough nerd calculation. Let's see. I can't see if people are laughing or sleeping or whatever, so it's hard. But the driving forces that come into play that make air pressure differences in homes. We talk about the wind, we talk about the stack effect, but very, very relevant here are, of course, the mechanical fans. So the fans are, really the biggest driver of air movement. Okay, moving on. Also, let's just get this out of the way up front, Joey. The single biggest design decision that you can make that will impact the efficiency of your heating and cooling is where you put the ductwork in the mechanical systems. And I feel like all these design decisions work their way into home design or home renovation, and I'm just like, are you really appreciating how important this is? So we've hammered this before, but in a nutshell, if you have a duct system in each of these three homes, and there's one up here where X is located, and there's one down here where Y is located. House number one, both duct systems are outside the conditioned envelope. House number three, both duct systems are inside the conditioned envelope. If everything else is equal in here, house number three is going to outperform. And it's because the ducts and the air handlers are inside. So I think with that, I'm just going to kind of click through and keep going here. I wanted to spend a little time on this. And for many of you, you understand this. This is a little bit, like you said, remedial, but it may be a little bit of enlightenment for some folks. How does an actual mechanical system really work? And this is a nice little, not too complicated diagram. Basically, if it's the summertime, we're pulling air from the house through the return ducts, and it's being driven by the blower or the air handling unit. And the air handling unit is going to push it across the furnace, which is basically dormant in the summertime. So the air from the house is blown across the, in essence, turned off furnace, and then it's blowing across the evaporator coil, and it's cooling off, and it's also giving off some moisture. So the cooler, drier air is then put back into the house through the supply ducts. And then what happens on the refrigerant side, it's basically a loop of refrigerant, and the refrigerant is constantly changing phase from a liquid to a vapor to a vapor to a liquid, that kind of thing. And I don't know, I think we talked about this in the heat transfer one, how if you have a pound of water and you heat it and it's 210 degrees, if you add 1 BTU of heat, it goes to 211 degrees. If you add 1 more BTU of heat, it goes to 212 degrees. But after that, you start adding all these BTUs, it doesn't go to 213 degrees. It starts changing phase. And in fact, to make all of that liquid water, 1 pound, about a water bottle's worth, change into vapor, it takes 1,000 BTUs. So it takes 1,000 BTUs to turn a pound of liquid water into a pound of steam. And likewise, a pound of steam turning back into liquid, 1,000 BTUs are going along for the ride. So there's a lot of energy transfer due to the phase change of, in this case, water, but inside your air conditioner, another refrigerant is used. So the compressor, which is outside, is always moving vapor. So it's actually sucking a low temperature, low pressure vapor, and it's compressing it to become high temperature, high pressure vapor. Then that high temperature refrigerant goes across the outdoor condensing unit coil, the outdoor coil, the one that you can see. There's a fan that's basically pulling outside air that might be 90 degrees and picking up heat from that refrigerant, and then the air leaves at, I don't know, 110 degrees. The refrigerant, in the meantime, you're dumping a lot of heat out of it, so it changes phase, and it changes from a high pressure vapor into a high pressure, high temperature vapor into basically a high pressure, high temperature liquid. And that liquid line then goes into the inside. This is supposed to be a metering device. It's usually, of course, inside your coil here. And that liquid meters from a high pressure liquid to a low pressure liquid. It boils and it comes out cold. So it's low pressure and it's cold. And then, of course, you're moving house air across it, and it's causing that refrigerant to boil out again, and the vapor is now leaving. So that cycle, that refrigeration cycle, is a magical thing, but it allows us to actually, to some extent, you might say it defies physics, because heat is always trying to go from its hotter outside to its cooler inside. But you can make it go the opposite direction if you pump it. In this case, you're pumping it with this compressor. So we're not violating any thermodynamics, because the refrigerant is colder than the house air here and hotter than the ambient air here. So it's a magic system. You could just think of fairy dust making it work. I don't know, but I think it's pretty amazing. I marvel at the refrigeration cycle. So having said that, what is the purpose, Joey, of an HVAC system?
Really, it's about comfort for the occupants. When we think of comfort, obviously we think about the temperature, we think about the number on our thermostat, but it also provides moisture control as well. So, and we'll talk about sizing and how that affects moisture control as we go along. Also, air filtering is nice. We talked about, all that a few weeks ago. Filtering is great. Don't get me wrong, but it should be one of the last things that you do as far as indoor air quality goes, and ventilation can be tied into the HVAC system as well.
Yeah, so the standard filter, the 1-inch filter, is really not there for you. It's just to protect tennis balls from getting into your coil or something. So large sticks or things like that. So anyway, yeah, I think that's important. And as you mentioned, hopefully we'll get it to come back here. How does it actually work? Whoops, it went too far. I knew that was going to happen. I think there's a little lag here, so there we go. All right, I'm gonna try it one more time. Apologies for that. This is actually a prop that we have that's a functioning split system. It's got a furnace below it. This is at our training center. And I remember one day we kept talking about what was happening inside this box. And finally I realized, like, why don't we just put a window on this? And so you can actually see it run, and you can watch condensation form and things like that. So let me kind of walk you through what you're looking at. So first, don't get confused by these two larger PVC pipes. Those are for the condensing furnace, which is below it here. The bottom of this condensing furnace, where you can't see it, is where the blower is, the air handler. But the box behind it here that has a window on it, this is the skinny line right here is the discharge line, and the fat insulated line is the suction line. Those are the two refrigerant lines going to and from this indoor coil or this evaporator coil. You'll notice the coil is shaped, it's called an A coil because it looks like an upside down letter V. I don't know why they call it that, but anyway, it's got refrigerant inside tubing, and of course the tubing has fins on it. And this little octopus looking device here is or it looks kind of like a squid, I guess. It's the expansion valve. So this is the metering device that controls the amount of refrigerant that you're trying to, you don't want to have too much refrigerant and fill up the coil with liquid. You don't want to have a dry, or all vapor coil either. So the refrigerant comes in at the bottom of the coil, it's completely liquid, and it leaves the top of the coil completely vapor. That's what it's supposed to do. And this device meters that. So when it operates, the warm, humid air from the house is blown across the fins, and it comes out colder. The thicker the coil, the more fins, the more surface area you have. You have more surface area to not only cool air, but also to, of course, have condensate occur. And the drop of condensate finally, this one hits this one, and this one hits this one, and they drip down, into a pan that's at the bottom. And after a certain amount of time, you get enough liquid in there that the liquid level rises up enough, and it flows out this little PVC pipe, which is the condensate line. So the important thing here, and Joey, maybe you can elaborate on this, is that the system has to run a long time in order to remove condensate.
Yeah, so that pan.
Well, that was my setup.
Yeah, sorry, you lagged there for the last minute. So the pan fills up with water and then drains out that little condensate line. But it actually takes a little while for that pan, the water level in that pan, to rise enough so that it actually, uses that drain line there. So it does take time. So again, keep teasing the sizing issue. Maybe it'll come up here in just a minute or two.
Yeah, and the point too is that it probably takes about 15 minutes for this to hit steady state. And until liquid water physically leaves out this pipe, you really have not done any dehumidification, because the air or the moisture, if it's still on the coil, will just re-evaporate. And if you left your fan running all the time, it would really re-evaporate. So we don't typically recommend that you do that unless there's some other reason. So, very good point. And I think people have understood, we probably have talked about this, how the thing that measures air temperature on the wall is only a part of thermal comfort, because it's also the amount of moisture in the air, as well as, is air moving across my skin, and what are the surfaces surrounding me like? So the mean radiant temperature. So we've covered those in other webinars, but just appreciate that the thing that drives air conditioner is only looking at one of 4 things that affect your thermal comfort. Okay. Hopefully we're still driving. This is a great one. Joey found there's a million versions of the psychrometric chart, but I thought this was just kind of worth mentioning. And I'm going to try something here. If you can imagine that I just think it's interesting as a species, our acceptable level of indoor comfort temperature band is really pretty small. You know, where if you kind of say, okay, 75 degrees, most people are going to be probably happy in there. I'm willing to go, you know, 6 degrees cooler, and I'm willing to go, oh, I don't know, 6 degrees hotter, and that's it. That's my temperature band. I'll go between 68 and maybe 80. And for some people, they're like, no way, I would go plus or minus 2 degrees. But the other thing that's interesting is there's a sort of a too dryness factor and it's a too humid factor. Now we can still be comfortable if it's humid, but obviously from a sort of not growing thing standpoint, I would say we certainly want to be below 60% relative humidity. And then the same thing on the dryness side, we can be quote comfortable down around 30% relative humidity, but you know, really and truly, we talked about how viruses, you know, they kind of are, you can kind of keep them at bay if you're above 40%. So all of a sudden, you know, we're drawing our box here of comfort. You know, I don't want to grow viruses, and I don't want to have dust mites. So, you know, this little box starts getting smaller and smaller and smaller in terms of our comfort window or our comfort, you know, sort of envelope that we're going to be, you know, good inside of. So it's a kind of a fascinating thing that you can look at what happens. I thought I don't know if I'm going to go here, but these diagonal lines are looking at enthalpy, which is a way of measuring sort of the heat and moisture content of air, and there's a, you know, you can do some calculations on this. So if you know, sort of start here at one point on the chart, and then you end up at a different point, you can calculate the change in enthalpy, and there's that's accounting for both the moisture removal as well as the temperature change. I think that's enough said on that. So let's drive down the next page. Hopefully this will work. There we go. So again, just to reiterate, you know, the sweet spot seems to be about 50% relative humidity. That seems to be a good place to be at what temperature? At room temperature, which is typically in the, you know, low mid 70s, somewhere in that ballpark. And if we stay there, we kind of keep everything else at bay. And then let's see. I'm sure some people have heard of these terms. It turns out that the work that an air conditioner does is really two types of cooling: the sensible cooling and the latent cooling. The sensible cooling is simply the temperature change of the air, and the latent cooling is the moisture removal component. And just so everybody knows, sensible is easy. Latent is hard. Latent is the reason your air conditioner has to run a long time and have liquid water drain out, because it's just hard to do. So if you're in a humid climate, you're going to find that you tend to have more challenges with the latent load. Again, it's easy to cool air down, it's hard to dry it out. So the other thing is that the two loads make up what's called the total load. So I'm just going to make up some numbers. If I just hypothetically had, you know, let's say 24,000 BTUs, that's a 2, and that's a 4. And I had 12,000 BTUs of latent. That was my load. Let's see if this will work. And I'm gonna make that 2 look more like a 2. There you go. And so the total would, in this example, be 36,000 BTUs, or kind of speaking in rough terms, that's a 3. This is fun. And should we mention, Joey, that this artwork will be on sale in the lobby? So the sensible load plus the latent load makes up the total load. And there's also a term you may hear called sensible heat fraction or sensible heat ratio. In this example, in the way it's calculated, it's a sensible load divided by the total. So it's really saying what percentage of the total is temperature cooling, and we know the rest is latent cooling. In my example here, it would be 2/3, or 67% of the cooling load is sensible, and the rest is latent. So probably the big takeaway here is that you want to make sure your indoor coil has been tested with your outdoor condensing unit. and that's called a matched coil setup. And by that we mean you're not using some fly-by-night, untested coil with just brand X condensing unit. We actually know how it will perform because it has been tested. Anything you want to add to that?
Yes, if there's any homeowners or anything that have ever experienced this, when it's time to have their HVAC system worked on, they're going to try to sell you both coils. But in most cases, they're doing the right thing.
Yeah, generally you want to match. Yes, I would say that is correct. And then that's probably enough said, I think, at this stage. We'll try to talk a little bit more about coil. And okay, so into equipment and duct sizing. So beginning with the equipment, I'm hoping that I clicked it. Maybe I didn't. There we go. Rules of thumb. And
Yes.
that's enough
Speaking of
said.
the HVAC
Rules
contractor.
of thumb are challenging. Go ahead, Joey.
You were breaking up there a little bit,
So
but
apparently,
I
I
just
don't know if
said
you can hear me, but we found this on a
Mike, your voice went out there a little bit, so I'm gonna explain this one and we'll
yes,
see if
I'm back.
okay.
I think this is just to say don't use rules of thumb. So let's advance onward. And I stopped talking there for a second. So however, there is a process: ACA manual J, ACA manual S. There's an ACA manual D for duct design, and that we thought we'd just fairly quickly say manual J is used to calculate the cooling and heating loads. Manual S is the process by which we select an actual air conditioner that will deliver the goods. It will be able to satisfy both the sensible load and the latent load. Hopefully this will advance. Okay, so Joey, I'm assuming you can hear me.
Yes.
What is it looking at when you do a load calc? It's basically looking at where is this house located? What's the climate like in that location? Which way is the house facing? What are the components that make up the thermal envelope? That would be how much insulation is there, how much surface area is there, what are the windows like, and so on. How leaky are the ducts? How leaky is the house? Where are the ducts located? What kind of internal gains are happening? Typical appliances like refrigerators and things that give off heat. And do you have any ventilation being, if you have 50 CFM of outside air being brought in, what's the impact on the load? That kind of thing. It all kind of starts with this idea of design temperatures. And so there are indoor design temperatures, which for the most part, we choose 70 in the winter and 75 in the summer. Those are the defaults. That's what we're trying to make the indoors be in different seasons. And then there's outdoor design temperatures, which are a function of the climate that city is located in. And if you do the math, there's about 8,800 hours in a year. If you do 365 times 24, you'll get about 8760, I think. So about 8,800 hours. And if you kind of said, a fourth of that is heating, a fourth of that is cooling, but let's maybe even be generous. Let's just make the math easy. Let's say 2,500 hours is air conditioning and 2,500 hours is heating. It's not necessarily that. But what happens is they look at the statistical weather for a city and they kind of go, okay, there's a temperature value outdoors at which it's only colder than that 1% of the hour. So about 25 hours of the year, it's colder than 24 degrees on average in Atlanta. And likewise, in Atlanta, it's only 1% of the hours, about 25 hours out of the summer on average, is it hotter than 92 degrees outside. And so we're using the almost hottest day and the almost coldest night of the year to calculate as our outdoor design temperature. And then we get a delta T across it. So the 70 minus the design temperature and the 92 minus the indoor design temperature. And that's the delta T's that get used when we do a load calc. So it's that UA delta T calculation that we talked about in some earlier webinars. And I think that's probably enough said on that. So in essence, here's what happens in a winter load calc. We do it at nighttime, so we're going to get 0 solar gain. We absolutely ignore all of the interior gain that we're going to have from appliances. So this is a really worst case scenario. And we do UA delta T heat loss through the walls, the windows, the doors, the floor, the ceiling. We add something for the leakage of the house. We account for the ducts, and we add it all up, and that adds up to be, let's say, 37,252 BTUs per hour. And our job then is to select, let's say, a furnace that will be able to deliver at least 37,252 BTUs an hour. That's how it works. And you can oversize the furnace a little bit and still be well within good graces. In the summertime, it's the same thing, only the heat flow is going a different direction. It's going from 92 to 75. It's gaining into the house. It's got a higher delta T across the attic. And we are now going to account for the solar gain through the windows. And we are going to account for the internal gains of the lights and people and appliances and so forth. So a cooling load is a little more complicated. And again, it's the almost hottest day of the year, but it's not the hottest day of the year. It's statistically, the almost hottest time of the year. So that's going to be our process. And again, we'll add the loads from each room, and that will give us the total load, both sensible and late. Today, we typically are using software to do this. And, if I think we've covered a lot of this, but if we do oversized equipment, we're going to pay more for it. It's probably at least $1,000 a ton if it's oversized. It's going to, if it's too big, it's going to short cycle, and that's not going to be good for the life of the equipment. And that's also not going to be good for moisture control. So in this example, that could be what's happening in this house. Condensation on the supply register. In terms of load calcs, without going into it, probably people have heard the term garbage in, garbage out. It's a tool. Manual J is a tool. If you put in garbage numbers, you can make it spit out whatever load answer you want. So it's a tool, you got to use it correctly. And we've definitely seen cases of people either accidentally or on purpose putting in wrong information. I saw a load calc that had Atlanta's outdoor design temperature of 110 degrees. I saw a load calc that had a 3-bedroom house with 15 people in it. And all the windows faced west, and the windows were all single pane metal frame windows. And I don't know, leaky, I'll just pick very leaky, and that will have a big impact on heating. So these are just typical things. So it's a tool, you got to use it correctly, and then you should be in good shape. We do work in other states. I thought this was great. I'm sharing some data from about 80 homes in Missouri that they found. This is a beautiful bell curve of data here, and you can see the median was right around 1.5 tons oversized. Pretty amazing there. So that's a significant additional first cost, and obviously some performance issues as well. Okay, Joey, I'm driving on. Talk to me if you want to say anything.
Sure thing.
Manual D is it's the process by which we design a duct system, and it starts with a room by room load calc. So we know the heating load and the cooling load on this room right here, and we can back out what is the CFM for heating and what is the CFM for cooling, and the bigger of the two is what we will design the duct for. So each room essentially is designed with a duct system to deliver the bigger CFM of the heating or cooling. So that's the first step. Again, typically we're going to do this with a tool, software, or an old school ductilator. And I just thought I'd show an example. Like here, bedroom number 3, its heating load is 2,000. Its cooling load is about 1,200 BTUs. And the heating is the dominant CFM. So you need about 68 CFM. And the software is saying, I think you can do that with a 6-inch flex duct. If you look down here at the kitchen, you can see that The heating is pretty small, 400 BTUs an hour. The cooling is bigger, 1600. Cooling is the dominant load, and you back out and it's almost 90 CFM. So it says, okay, 6-inch is not big enough. You need a 7-inch or an 8-inch with a damper. That's kind of the basic rules of how the duct design process works. Waiting, there we go. So is this important? Joey, are you there? Can you hear me? Because I was walking through a $1 million house and I took this picture on the left, and I call it Ductopus. And recently a colleague sent me this picture. I call it Ductopus Prime. It looks kind of like a transformer, doesn't it? I don't know.
Yes.
Okay, well, I'm laughing at my joke. I don't know if you are.
I'm
Yeah. I just think it's really sad. This was a $1 million house and it had the cheapest, crappiest mechanical system you can imagine in it. And they're really, I don't know, you can't fix this. You're gonna have to just rip it out and start all over again. It's so bad. So it's kind of sad. And we really, that's partly why people oversize. There's other duct design issues that you should be aware of, like not putting your supply within 3 inches of your return. You're not going to get good circulation. Try not to do homemade duct fittings. Those that does look like something I would do. But we've also talked about this issue in some other webinars where we have the main return in the hallway of the house, and all the bedrooms have supplies but no return path. So when we close the bedroom doors, the bedrooms go positive and the main part of the house goes negative. And that can drive infiltration and exfiltration and create comfort issues. So here's a great solution, this jumper duct. And I love it. Did you take this picture? I love this photo here, where you can see we're in the hallway here. If that door is closed, the bedroom air being supplied in has a way to get back to the hallway through this little jumper duct. It's a great picture. We also talked about options like an undercut, and my rule of thumb is you need about 1 square inch of opening for every CFM you put in. We never seem to have enough with just a regular undercut.
Did you just
transfer
use a rule
duct
of thumb,
through
Mike?
the wall? I did, but some rules of thumb are not so bad. But I'm just saying that we're really trying to minimize the pressure drop between the bedroom and the hallway, for example, if the door is closed. So yeah. Okay, Joey, I love this picture.
Yeah, so we're going to talk about, where to put the ducts, and Mike and I both have some strong opinions on that. And anyone can look at this duct system and say, oh, wow, that's wrong. We are locating the duct system outside the conditioned envelope in what Mike called a extremely well vented crawl space. But I don't think that putting a duct system in a 130-degree attic is any smarter, to be honest. So we see these things as being obvious, but anytime you put your duct system outside the conditioned space, I think it basically looks like this in my head.
Yeah, is that more raccoon proof or less raccoon proof than the one in the attic? I'm not sure. So all right, I made a collage for everybody. I hope you appreciate my artwork skills. How can I locate my ductwork inside the conditioned envelope? Well, I could put it inside a conditioned basement or crawl space where I've insulated the walls of the crawl space or basement. I could put it inside an attic where I have foamed the roof line. I could do a fur down detail in a hallway, for example, where I've got a hard air barrier, and then it dropped the hallway drops from 9 feet to 8 feet. I could essentially have a space to rough in my duct system after putting in a hard air barrier. I could do kind of a drop soffit that goes around a room. And whenever you blow air out the sidewall, like you see in this picture here, and like this duct system probably has as well, you do want to make sure your terminal device is designed correctly to be able to throw the air. It'll actually cling to the ceiling. I think it's called the Jumanji effect. I could be wrong on that one, but you can also frame it with a truss where the bottom cord does not go all the way across. it's you know, a bump up is created, or it's kind of a form of a scissor truss. And this was a builder in Florida that was doing what they called a plenum truss, where they frame their house and not build the interior walls yet, set all the trusses, put a hard air barrier, and that creates this space where they can rough in all their ducts. They're going to put a finished flat ceiling in here, and then all the ceiling light fixtures and ductwork are in that interstitial space. And if you think about it, they have the same benefit of the spray foamed attic, only they used a much less expensive insulation here. So a pretty impressive design concept. If you're really good and you really pay attention to it, you have to really coordinate with the subs. It is possible to run ductwork between the first and second floor, and you blow the supply air up for the second floor and down for the first floor. You just really have to coordinate and design and make sure that the plumber doesn't run their pipe, you know, where they're not supposed to. And then my friends finished out their basement. They used exposed ductwork, so that's another option. So there are lots of ways to get the ducts inside. Please try to avail yourself of one of those design options. In terms of really making it work, it's great to take your duct design and then commission it. And we commission it by using a flow hood, and we can verify that we're getting at least within 10% of the design airflow. And we might actually invest $2 for a balancing damper on each supply run, so we can really adjust the airflow. It's like, that's crazy. What a crazy idea. We'd put dampers in our system. So how do we, what materials can we, but there's really 4 types of duct materials. There is metal ductwork. Round metal, there's also square metal or rectangular. Metal duct, you know, certainly has some good advantages. It's very durable. It's also very expensive. Flex duct, which has probably replaced it, has some advantages, but also you probably wouldn't be doing this with metal duct, what you see in these 2 pictures. There's also duct board, fiberglass duct board, which has the silver lining on the outside. It's interesting, that's the pressure barrier. That's where you want to have the sealant, is on the outside of duct board, but on flex and metal ductwork, you want the sealant to be on the inside. So we'll talk more about that. And then there's the 4th category, which is building cavities. And we've talked a little bit in other webinars, but that is essentially where you're using wood or a wall cavity or a floor cavity or something that you built as a duct. And that is not a good idea. Those have a very bad track record and get violated frequently. And Georgia was ahead of the game on this. We banned these in our code in 2011. The more recent versions of the Energy Code have also said you cannot do this. So in a little more detail, metal ductwork is the smoothest, least resistant conduit for making air move. Any kind of fluid moves the smoothest in a straight round metal duct. And what's good about it is it's very durable. It requires you to actually usually do a design and think about where things are going to run. And it's got a lot of good things going for it. It's also expensive. It also has lots and lots of leak seams that need to be sealed with mastic. You got to screw it together. It's certainly the most expensive duct system out there. And it doesn't come with insulation. So you got to, on top of everything else, you got to wrap it with insulation. But having said that, I really worked hard to keep the metal ducts that came with my house. They were in bad shape, but I fixed them and I get really good airflow. So I got to say, I know a company, I have a lot of respect for these guys. They come in and they will just take out the old duct system and put in new flex, and they design it and they do it right. So to their credit, they end up with a system that works well. But I like metal ducts. What can I say? So Joey, flex duct, 3 main parts. You want to cover these?
Yeah, I like this picture because you can actually see all 3 parts here. The first is the inner liner. So that black plastic type material that you're seeing, that is the air barrier. But you'll also notice that it has kind of this wire, to kind of give it some structure. Yeah, slinky. And if you don't put the flex duct in there correctly, that slinky there will kind of make the what I call speed bumps, and that'll definitely slow down that air. And you know, you want something nice and smooth. The second part is the insulation. I think we can all recognize that pink fiberglass. That's going to be our thermal barrier of the insulation. And then that outer liner acts as the vapor barrier. And if you want to call it, you can say it's a radiant barrier as well. But we're mostly interested in the vapor barrier portion of it. So
Yeah, and that reminds me, I don't know if anybody's from North Carolina in here, but North Carolina does a lot of things really well. But one thing they do that's really stupid is they run a lot of black ductwork up in the attic. So I'm going to say if you have ductwork running in an attic, it needs to have a silver lining on it. Just think about why that is. Okay, it's not a lining, a silver outer jacket. Flex duct is really, originally it was intended for very short runs, like we run a trunk, we run a branch, and then the last 5 feet we connect with flex duct. And then someone sort of said, well, let's make the flex duct get rid of the branch, and let's make the flex duct get rid of the trunk. And that's where we ended up with today. And it's not the same. But if you actually pull it tight and support it properly, and you can actually get airflow through flex duct, so it can be done right. It's very easy to not do it right. A good rule of thumb, and this is an okay rule of thumb, is to upsize the diameter. If you need a 5-inch metal duct, use a 6-inch flex duct. Up in the diameter 1 inch is going to help alleviate some of those problems. And you know, it comes in a box that's 25 feet long. So hoping my, there he goes, that if your duct is, you know, you're trying to connect, say, between a fitting that's about 8 feet away and use all 25 feet, not only is this 25 feet of resistance, but I think we mentioned before that if you turn air at 90 degrees with a typical elbow, it's adding like 15 to 25 feet of equivalent resistance. So this duct is now several hundred feet long effectively. So yeah, that was another $1 million house I took that picture in. So I think you mentioned this. This is a great example of kind of showing if flex duct is really pulled tight, you're going to get about 15 to 20% less airflow than the same diameter round metal duct. I know that's square. If flex duct is just sort of laying there or you know, in any way kind of run poorly, you're going to get a way less airflow than 15%. So you're going to, you know, get 30% less airflow or 40% less airflow or half the airflow. And here's a great picture of you know, this smooth long radius elbow is going to help air turn nice and easily. This one is really, really hard for the duct system. That should have fittings on it. So that's a great example. And then to kind of wrap up, let's see, ductboard. You know, I don't know. I wish it had silver on both the inside and the outside. That I would be a lot happier with it as a product. But the main thing is that you seal it from, you want to air seal the outside of it. The foil is the air barrier. And you got to use collars and the right kind of collar and the right kind of you know, fitting to connect to it. And it requires, you know, good air sealing and just doesn't have the best durability track record. And then here's some pictures of where, again, we don't want to use building cavities as a duct, like a toe kick or a wall cavity or a wall cavity or a shelf that is being used as a return duct. Just stay away from that. Bad things happen with those. Who would ever put a light fixture in the middle of a duct? I can't imagine that. And yet I have pictures of it. So that's the problem with using floor framing as a duct. Somebody else feels like they got to bust a hole in it. So that's not a good thing. And by the way, that is not a legal sealant right there that we're looking at, the gray cloth tubing. This is another good one. I love this picture. And this is a return, I should mention. This is a return duct. So it's under negative pressure. So what is it? Any indoor air quality concerns with this? I don't know. Maybe whatever's stored right here being sucked in. Also, this is, if you have old ductwork, you might see this is called wheat tape, and it might contain asbestos. So the best thing you can do is just to take mastic and go, you know, put it right on top of it and squish it. The mastic will essentially make like a plaster cast around it, and then it won't get airborne. So, you know, don't disturb it, but just if you goop mastic on it, That's actually a good way to sort of make that safer. Okay. I think we have some opinions about using tape as a sealant. Here they use tape as a sealant and it did not work. The code actually says you may use UL 181 listed tape or UL 181 listed mastic. And they do not allow what they classic duct tape. So here's a picture of mastic. This is the material that we definitely endorse. I use it for a lot of other projects. I like the kind that has little fibers in it, but if it's a big gap, you can also use the same kind of scrim tape you would use for a drywall mud joint. They also make a mastic tape, which is a thick tape. It's very expensive, but it is, you'll know it's thick. And then there's regular UL 181 tape, which is also permitted, but we're going to suggest don't use it. And in Georgia, it's not allowed to be used as a sealant. So that was something we amended our code to do. And again, the one tape you absolutely cannot use is gray cloth duct tape. So mastic tape, those are okay. All right, and as our friend says, please don't put tape on ducts. Okay, all right, no one laughed, so I'm gonna drive on. Putting sealant is pretty important. So it's all about where's the pressure barrier and making sure it's done continuously. With flex duct, you can do it from the outside, like you're seeing in this picture here, but a lot of times when you're assembling it, it's probably better to put it on the fitting and then slide the flex over it and then put the zip tie and then fasten the zip tie. I thought maybe you were going to say something, so jump in if you want to. The other thing is, you know, we always recommend you inspect some of the fittings like Ys and things like that, because, you know, this is people getting lazy and it's like, I'll just cover it up with insulation, but you can see no sealant was used at all. And also, if you look at the amount of crimp, see this distance right here, you can see that this zip tie is actually off of the duct right there. This is going to disconnect in time. And then there is actually a special tool that you would use to attach flex duct with a crimping tool. I've done it with a pair of you know, vice grips, and you know, you cinch it and you disconnect it, reclip it and cinch it and so on. So it can be done, but the tool is definitely the way to go. It's a lot easier and it'll cut off the excess when you're done.
And there's a good example of that blacked duct that you were mentioning earlier.
Oh yeah. So I don't know where this duct is located. If it's in an attic, don't do that. That's my advice. Okay, driving on. Again, if we see mastic on the outside of the duct, of the flex duct, we start to get suspicious, because that means someone's trying to either fool the code official or doesn't know what they're doing. So it's the inside pressure liner that matters, the inside seams of metal duct that matter. And you can retrofit sealed ducts from the inside if you have a boot and you have flex duct connected to it. Reach inside. I usually use a glove in my hand and just goop mastic from the inside and seal all the seams. But this is the main connection that we're really trying to get, as well as all these little seams. And of course, seal it, the boot to the drywall. And of course, with DUCTBOARD, we want to do the outside. Georgia says if you want to assemble DUCTBOARD with silver tape, that's fine, but you're going to have to cover it with mastic to seal it. How thick? Thick as a nickel, about 2 millimeters thick. So the edge of a nickel is the thickness you want. And then of course, where is the pressure the highest in a duct system? Right there at the blower. So even a small leak at the air handling unit is a big energy penalty. On existing homes, we recommend you pull the registers, vacuum out the inside, reach in as far as you can with mastic and a glove, and start sealing and work your way out. And then, you know, put the register back on, and then seal the boot to the subfloor, or to the wall in this case. Supporting the ductwork with straps is important, as opposed to, I've seen some people hang it with like a coat hanger wire, and that's going to pinch the duct and the insulation. Let's see, I think we're Joey, anything you want to add on this? It's not the
Yeah,
most beautiful duct.
exactly. We had a similar picture go out with some of the communications for this webinar, and someone had emailed back and said, well, technically that isn't correct. We know, obviously, we use a lot of stock images, and stock images generally aren't taken by home inspectors or HERS raters and such. So what I wanted to say here is that, if you get your ductwork inside the conditioned envelope, which, it is in this case here, don't forget the fundamentals. Don't just think, oh, well, it's in the conditioned space, it doesn't matter. Yeah, I'm not going to worry about sealing, and I'm not going to worry about hanging it properly. These pinches and things, they don't really matter, because obviously the rooms aren't going to get the preferred CFM numbers if you have these pinches and these tight twists and turn like you see here. So definitely not a good example of a good system here. And this one
Good
here,
point.
someone had asked about this in the Q&A here. So R8 for anything 3 inches and larger, R6 for less than 3 inches. I think R8 is probably just a good practice. And then even if you have a duct system that's going inside a conditioned space, such as a spray foam roof line that we looked at earlier, then go ahead and put some insulation on that anyway. And Mike, if you want to tell us why, I think
Yeah, it's not going to save any energy, but it is going to not have a cold surface that could sweat. And so the idea that you don't have to insulate a duct if it's inside the envelope, I get it from an energy standpoint, from a heating standpoint, sure, no problem. But from a moisture concern standpoint, I want all my ducts to be insulated. And I
yeah,
believe it's R8 for ducts in an attic too. I think it's R6 for ducts elsewhere. And maybe they changed that for the 18, but I know it's R8 if the ducts are in an attic. So that's easy to look up. I'm going to kind of wrap us up here with talking about duct testing. And I'm going to explain this one by saying, here's a house that I'm just going to use a 2.5 ton air handler on here. So that's about 1,000 CFM. If you have supply leaks, you pull 1,000 CFM from the house, you throw away, let's say 100. That means only 900 goes back in. The house is getting 900, but you're taking out 1,000. So your house pressure goes negative. And over here, all the supply air, all 1,000 goes into the house, but you're only taking out, say, 700 because of 300 CFM of leak on the return. That house is going to go positive. You can do this test. I bet people on this call, I know some of them have blower doors. If you have an accurate pressure gauge, you can just run a tube outdoors. If you're set up a blower door, you just put the fan, put the cover on the fan, and I recommend you zero the gauge, baseline it, make it read 0, and go over to the air handler and turn the fan from auto to on. It'll make the blower turn on, and watch your pressure. If your house pressure goes negative, it means you have a lot of supply leaks. If your house pressure goes positive, it means you have a lot of return leaks. Joey, what does it mean if you turn it on and the pressure doesn't change? What does that mean?
it must mean that you have a perfectly balanced system, right? There's no
Well, that's
other
possible.
possibilities, right?
There is another possibility.
What would that
Right.
mean?
That possibility would be you have equal leakage on both sides. So if
Mm,
you're leaking the same amounts on both sides, if it's 0, that's great, but it could be otherwise. So this is sometimes called the dominant duct leakage. So just really quickly, if this air handler is blowing 1,000 and it loses 100, that means 900 goes in. But because of this return leak, 300 from there, only 700 from the house. The dominant duct leak in this case is the return leak. It's the bigger one, so the house pressure is going to go positive. So just be aware if these two arrows are the same size, then your leakage is equal on both sides. You're not going to see a pressure change. And it might be because they're tight, but it might be because they leak equally. So the codes have required duct testing since 2009. It was pretty easy in the 09 code. It was 12% leakage. And it would allow you to not have to test if you have the ducts inside the envelope. And it looks like they're considering getting rid of that in the future code. It's in there as a carrot right now. You can test ducts by the newest code today. It's you're allowed 4% duct leakage, and we'll talk about that in a second. Georgia backed off. We're actually 6%, but still pretty tight. And you can test ducts at rough-in, or you can test ducts at final. And what you do is you essentially mask over all the supplies and returns. You connect your little duct testing fan somewhere into the system. Here they're connecting at the return. And you pressurize or depressurize the ducts to the test condition, which is 25 pascals. And this is an accurate fan, and it can measure the amount of CFM. The amount of CFM it takes to pump up the ducts, if you will, to 25 is equal to the amount of CFM that's leaving through the leaks. So the code says you can have 4 CFM of duct leakage for every 100 square foot of conditioned floor area. So we would say 4% of the floor area is the allowed amount of duct leakage. So if it's a 1,500 square foot house, you'd have to come in tighter than or equal to 60 CFM, and that little subscript 25 is telling us that we're testing it at 25 pascals. Joey, a duct blaster, is this what comes to mind?
No, actually, I have a slightly different, yeah, that's more of the duct blaster that I think about.
A video game or something, but no, this is a duct blaster. It's a well-known brand of duct pressure testing equipment, and made by Energy Conservatory. There's also a good brand made by Retrotech, but I think everyone kind of calls it a Kleenex and uses that word synonymously, or interchangeably. So duct testing equipment. And we did want to point out that if you would like there's a very I think a pretty nice detail 10-minute long testing video how to do this with I'm sure a well-known celebrity is that.
But, a well-known celebrity with a mustache.
I think it was made about
everyone go and watch it.
10 years ago, and he was a lot younger at the time. Yeah, rocking the goatee. So in this, I think, whoops, it skipped ahead there, but we want to thank you as always. I think we made it to the finish line, and we really appreciate everybody hanging with us. And I think this is an amazing topic. We might even do one where we go deeper into Manual J, or tell us what you think. What do you want to talk about? And again, as always, we appreciate your supporting Southface. Here's some other great resources that you can get more information on. Joey, anything you want to add, and then take some questions? Or
yeah, I just want to let everyone know we're at 12 o'clock, so if you have to step off, we understand, but as per tradition, we usually stay on for at least 15 minutes or so and kind of answer some questions, and we have had a few. But before I get into your questions, we have a question for you. So again, as is tradition with these things, hopefully you can see that we've got a little poll for you here. So if you could answer that for us, just kind of give us an idea of.
And again, we're hoping that this will spur you to action. That's our goal, is that you don't just sleep through this, but you actually do something. And nothing is an option on your list. I do like that. That's good. All right.
Yeah. Well,
replace my HVAC system with a ductless. I will add exposed ductwork to my next design and charge more. I like this. You are having fun with this. Can we see the results?
Yeah, I think we've got enough people voted here. I'm gonna close and share. So people maybe have an idea that they're gonna do a little bit of duct sealing, and yeah, I hear the stats all the time that Home Depot is having their best quarter ever because a lot of people stuck inside are going to work on their house a little bit. So maybe that's something. You can get MASTIC at Home Depot. Typically, it's not going to be the best product you can get, but it'll definitely do the trick. So
yeah, actually, I'm glad you mentioned that. I was going to say, I was just going to throw in too that I like to buy MASTIC. You can buy MASTIC from an HVAC supply house. You do not. That's not a regulated product. You can go in, and I usually go in and pay cash or use my credit card or something. But you can buy a gallon of MASTIC at an HVAC supply house, and that's legal for them to sell it to you. They can't sell you an air conditioner, but they can sell you the MASTIC. And I also think you can get it online, but I figure if you can get it for 20 bucks a gallon, you're doing pretty well. At the big box stores like Lowe's, Home Depot, whatever, they're usually more expensive. So nothing wrong with getting it there, but it's I want you to buy a lot and use a lot. I always challenge people. I'm like, see if you can use 4 gallons of mastic. Just go crazy with it, and if you have leftover, I'll take it. I'll use it for something else. So.
Yeah, that kind of, when I was working in the field, we had a record of 21 buckets of mastic for a house. So, and that was
Oh, wow.
yeah, pretty good. So we got some questions here. First of all, of course, you offended some people from North Carolina by talking about their ducts. So how dare you?
I love North Carolina. We love you, Carolina. Explain to me why you're using black ductwork in an attic. Explain that.
Yeah.
I always give them a hard time about that. Fair
Someone
enough.
also chimed in about a fifth type of duct, and especially you might see fabric ducts being used in commercial spaces. We actually have some of that in our office at Southface, if the office still exists. I haven't been there in a while. So thanks for that.
That
Someone
is a great way to do. Yeah, for exposed ductwork, I think cloth ducts look really good, and it's a duct sock. Yeah, I think it's a great idea. And also, Joey, I didn't mention there are high velocity ducts which are made of PVC, and I kind of have I kind of see pros and cons to those systems. On the pro side, that they're usually well engineered and designed, because if you don't know what you're doing, you'll have noise issues. And the fittings, PVC fittings, are easy to glue up and make tight, so that's a good thing. On the downside, you're sort of pushing air through a straw, so fan energy is a concern. I think in certain applications they definitely make sense. So yeah, technically there are some other duct materials.
Yeah, and if velocity is a factor of comfort, if you stand under one of those or place one of those over your bed, you're going to be very uncomfortable because it's going to be quite a bit of airflow. Someone made some comments about AeroSeal. That is certainly an option when it comes to sealing ducts, but I think that's, in general, AeroSeal is a great product, but it's not always necessary. We can get there using more, let's say, easier materials and cheaper materials. But by all means, if you've got a couple $1,000s laying around.
Well, also if your it's a great system, and if your ducts are very inaccessible, it's brilliant. I mean, it's not going to typically seal a gap more than I think about half an inch ish. But it is a great way. It's kind of like Fix-A-Flat for a duct system, and look it up. It's a great product. I've seen it done, and it really does work. But there's a high setup cost to it. Once it's set up, you can just let it run and run until your tightness level is whatever you want it to be. And they have a similar product now that can air seal a house under construction as well. So very cool concept. But like you say, yeah, if you're not afraid to crawl or get your hands dirty, you can do it for a lot less money with 4 gallons of mastic, maybe 21. I don't know.
We've got a little bit of support from North Carolina. Coastal Community Action. The best weatherization in North Carolina does not use, that old black ductwork. So they use the good stuff. So I appreciate you chiming in there.
Yeah, only in an attic. I don't care elsewhere, but yeah, in an attic. Yeah. Good stuff. Good stuff.
Someone is asking, if you have to use flex duct and make a tight bend, would you use maybe a metal elbow for that?
Yes, I would. Absolutely, you can use fittings with flex duct, and that would be a good way to do it. Actually, Joey, I forgot. I was going to add this in. We have a prop of this. Somebody makes an aftermarket thing that it's a plastic clip that turns a piece of flex duct and essentially makes a piece of flex duct effectively into an elbow, and it maintains the continuous radius of it. And I don't know how prevalent that is out there, but we actually have that as a sample. So
yeah,
I see some really cool graphics.
Someone had a comment about this, and we didn't make it clear. In this case, the crawl space is unconditioned and outside the thermal envelope. We get questions about that sometimes, and we should have made it more clear. I apologize, but in this case, yes.
Yeah, I should have shown crawl space. Yeah, yeah. Sorry about
All
that.
right, all
You're
right. Let's
absolutely
see.
right. That should be outside the envelope.
The roof.
Good comment. Good catch.
Okay, and then I'm gonna, I think, step.
I like that people are critiquing us. This is really good.
Yeah, yeah, of course. We always appreciate that. Someone also had, I think we could probably just talk about this one
Well,
for several hours here. Oh, because there is so much information here, but someone was asking about this, I believe. If you're going to make this kind of fur down, where would the insulation be? Where would the air barrier be? Two air barriers, no air barriers. What are we doing here?
which fur down? Which fur
Uh,
down are we talking about here?
yeah, the one,
Sorry,
the one here on the right.
which picture? The one in the hallway?
Yes.
Yeah, the one on the right. And I've got several versions of that. We did a bunch of work with affordable housing groups, and they're smaller homes, and it really is a pretty easy way to really minimize the ductwork. And I was talking about having done this in Atlanta, and I want to say it was some Habitat affiliates in Florida, and they sent me some pictures of what they had done. And they said, they were blown away by how little duct material was. Like they're like, yeah, it was a little more work for us, but it actually was like so much cheaper from a duct standpoint. They were running heat pumps, so it was really easy. Some people put the heat pump up in there. Some people put the one we did, we put the 90% furnace in the closet right here. So the return duct was about 5 inches long, 4 inches long. That was it. That was the return. But the supply went up into this kind of a fur down space. So
Yeah.
you can use anything for a hard air barrier.
Hmm.
Here, it looks like they use chipboard, but for the affiliate I was working with in Atlanta, we were like, you're not dried in necessarily, or you don't have chipboard on site. Why don't you just use the OSB? You can
Yeah.
just use any sheathing material, and
Hmm.
just essentially all you need is something that you can seal. And then that's, just pay attention to the details. So yeah, that's good. When you have a soffit like this too, you need to be careful as well. I don't know what this wall is over here, but you need to be a little careful about that as well. So you just have to make sure your air barrier is truly continuous and sealed before you put your finished ceiling in, so to speak.
Yeah, that's the one thing that a lot of kind of advanced builders are doing is making that attic floor separate from the ceiling below, so that you have an attic floor that acts as your air barrier. And I've seen people use, different products, like the something that you can make it into an air barrier, and tape and seal the joints, and then that way you don't have to worry about light fixtures or ducts or anything that has to penetrate that ceiling.
Right. Yeah. I mean, again, it's about this is a design effort here, and it takes some coordination. And we used to, be big advocates of running the ducts between conditioned floors, and I still am. It's just
Hmm.
that in the real world, you've got to coordinate. You've got to really design your plumbing ahead of time, and you've got
Yeah.
to design all your duct locations ahead of time. And this is where, like Revit might come in handy, or one of those BIM, building information modeling software packages, to make sure things don't conflict. So
Hmm.
you don't see that as much in homes, but I think that is a real thing. So
Where were
what
we
else we
when we
got?
were?
These are
I was, sorry if
while
this
you're
is
looking for questions, while you're looking, I was going to comment that if you had to pick a project that's like
okay.
a really impactful project on an existing home, this is definitely it. Go after your ductwork. And like I said, you know, pull the registers because it's easy, uh, especially if in the floors, ceiling. It seems like a lot of the homes that we're working on, the registers are in the floor, the system's in the crawl space. You can usually get to the air handler. So, even if all you do is pull the registers and seal boots as far in as you can reach, work your way out, and then you go and seal all the places at the air handler. And we talked some about that filter lock, a magnetic filter. thing, that those actions alone, even if you can't get to whys and things like that, just doing the air handler and the boots will be huge and very impactful. So
yeah, so easy. These are
okay, I was tap dancing. You got something?
well, I was going to say it's so easy. Maybe it won't surprise people. I've actually done this in apartments that I've lived in. So, yeah, you're welcome, landlord. So someone had a question about the toe kicks here, and is this allowed?
Okay.
I know we're still seeing this in the field.
Toe kicks are allowed if they are fully ducted. So there you go. The hard part
Have
is,
you ever
you can
seen
see
one
this
fully
one
ducted?
was installed. Yeah, exactly. It's like, you know, how do you get the framer to not beat to beat the crap out of this duct when they're set in the cabinet? And then they're going to cut an opening that is going to be way bigger than this, and then they're just going to shove it up there, and they'll put the register on it. So if you actually end up having to duct test this, you're going to have to mask over the register. You're going to see a tremendous amount of leakage. So you know, if it's fully ducted, it is allowed because it's fully ducted. But I'm just going to suggest, I don't really like toe kicks. I just think they're outdated, and I'd much rather just have it in the floor. And somebody was saying, I don't like it because it's in my kitchen and food fell in my duct. I'm like, yeah, well, you know, there you go. But it's what can I say? I have one in my kitchen, and yeah, you know, that's why we have dogs, to clean up the stuff that falls
There
down.
you go.
No, it's
Well,
just it's a great project. Something I hope that this does spur people to action, because it really does make a difference. And you know, the duct system is the lungs of your building. And you know, we just, the moral of the story here, the tagline for this webinar is duct love. Go in and love on your ducts, and good things will happen.
it's duct love, not
I'll
duct
mute
love.
myself after that. Right.
Okay.
Yeah,
Well,
yeah.
thanks everyone
DUCT.
for joining us. Once again, we're gonna wrap this series up next week, and then we'll have more news on the continuation, hopefully at that point. So thanks again. We hope you'd enjoyed it, and we'll be sending out the recording as well as the slides. Sorry for not getting those in earlier.
Thanks, everybody. Really appreciate it. And please feel free to send us emails if you you want to ask questions or chat about something else. Thanks again. Thanks, Joey.
Mhm.